Speedier than the outer layer of spacetime, it can stay aware of it, and it'll essentially tear. I'm frightened by this. At this point, our night sky is evolving quickly, and in a matter of a few years, while conceivably not sooner, it may turn out to be totally unrecognizable. Cosmologists, for the most part, are sounding the alarm. Specialists like Neil deGrasse Tyson have confirmed the inevitable impact of Polaris, and the story behind it is incredibly amazing. Polaris, known as the North Star, has for a long time been a constant in our night sky, serving as a critical reference point for stargazers, navigators, and space experts. However, this could soon change, modifying our night sky and infinite evaluations. We ought to delve into the significance of this danger and its implications for all of us. Join us as we uncover the narrative of Polaris as it gravitates toward its end. For a long time, Polaris has guided sailors and stargazers alike, standing firm as a guiding light. Its decided presence in the night sky has been fundamental for navigation. However, this stability may soon be disrupted. In September 2023, an investigation paper presented by the esteemed Royal Astronomical Society cast doubt on the fate of this brilliant light. Polaris is near the precarious edge of exploding, potentially disappearing from the night sky forever. Before we explore the consequences of this revelation, we must first study Polaris. Known as the North Star or Pole Star, Polaris is unique due to its proximity to the celestial North Pole. Positioned directly above Earth's North Pole, it appears nearly fixed in the northern sky and is situated in the constellation Ursa Minor, or the Little Dipper. Polaris shines as a moderately bright yellow-white supergiant star, much larger and brighter than our Sun. It is not a solitary star. It is part of a complex triple-star system, with Polaris A and Polaris B forming a binary pair while Polaris B orbits them. The interactions between these stars create gravitational forces that shape their orbits and influence their behavior. Any disturbances in these interactions can lead to irregular variations in the star's brightness or pulsation patterns. However, the specific mechanisms behind these interactions remain intricate. Polaris is located approximately 323 light-years from Earth, meaning the light we see from it today began its journey centuries ago. Thus, if Polaris were to explode now, we wouldn't see it for more than 300 years. It's even possible that Polaris has already exploded, and we are yet to see the light from that event. Throughout history, the North Star has held significant cultural, navigational, and symbolic importance. Its steadfastness and fixed position made it a valuable guide for ancient sailors, helping them navigate across oceans and lands. Symbolically, Polaris represented loyalty and direction, remaining constant amid the ever-changing night sky. For astronomers, Polaris served as a critical reference point, aiding the study of celestial movements and variable stars. As a Cepheid variable star, its periodic variations in brightness have provided essential insights into stellar properties and the nature of variable stars. This characteristic also played a vital role in determining cosmic distances and calibrating instruments. These pulsations follow a predictable pattern, which has made the star's behavior easier to anticipate. However, recently Polaris has deviated from this usual conduct. This irregularity in its pulsation cycle has puzzled astronomers, prompting closer scrutiny of this curious anomaly. Instead of following its expected pattern, Polaris has begun displaying unpredictable patterns of dimming, raising concerns among scientists that the star may be nearing the end of its life. This aligns with behaviors commonly observed in stars nearing the end of their life cycles. The ongoing expansion of Polaris' pulsation period, once stable, can be attributed to interactions within its star system. We've observed an annual increase in the pulsation length of 4.5 seconds, which may seem minor but holds significant implications. Some astronomers suggest that gravitational interactions between the Polaris stars could be causing these changes in its atmospheric conditions, directly impacting its pulsation patterns. Others are more concerned that it is near the critical edge of exploding. The similarities between Polaris behavior and that of Betelgeuse, another prominent star in the Orion constellation, are striking. Both stars have shown complex anomalies in their brightness, raising concerns about a potential explosion. Stars in their twilight stage often exhibit such irregularities before reaching the end of their life cycles. NASA has expressed heightened concern about Betelgeuse, However, formal attention has not yet been directed toward Polaris. As a Cepheid star approaches the end of its life cycle, it undergoes several stages, including the main sequence stage, the red giant stage, and finally the supernova explosion. Considering Polaris' erratic pulsations, scientists predict it has entered the stages of helium depletion, typical of giant stars nearing their end. These anomalies in Polaris behavior align with patterns common to stars in their twilight stages. However, convincing evidence of its imminent supernova remains elusive. Astronomers are closely monitoring these anomalies to understand Polaris' fate. If Polaris were to undergo a supernova explosion, it would likely be a spectacular event in our sky, potentially outshining the moon and becoming one of the brightest objects visible for days, weeks, or even months. Its appearance could significantly alter our view of prominent constellations like the Big Dipper or Ursa Major, of which Polaris is a part. Rest assured, Earth would almost certainly be entirely safe regardless of whether Polaris were to explode, given its mass and distance from us. While a Polaris explosion might not be as visually dramatic as Betelgeuse's, it could still be visible to the naked eye for an extended period, outshining nearby stars. Astronomers and observatories would undoubtedly take notice, sparking interest within the academic community and among stargazers. However, the impact on Earth's environment or natural systems would be less significant compared to a closer supernova event. However, what about Polaris itself? What will be its fate after a potential supernova event? We should clarify one thing. While giant stars typically end their lives with a supernova explosion, this is unlikely to be the case with Polaris. When a massive star goes supernova, a colossal explosion occurs within it, marking the final catastrophic stage in its life. This process involves a complete collapse of the core, triggering a violent shock wave that causes the star to explode. However, Polaris isn't massive enough to undergo such an explosion. Instead, when Polaris exhausts its nuclear fuel, it will shed its outer layers and transform into a white dwarf. This transformation will not result in a supernova but rather a quiet end as it evolves into a small, extremely dense stellar remnant. A white dwarf is the leftover core of a low or medium-mass star that has depleted its nuclear fuel. It's incredibly dense, about the size of Earth but as massive as the Sun. When this happens, we will no longer see its remnants from our planet as we see the star today. Contrasting the theoretical effects of Polaris explosion with actual supernova events offers valuable insights into the evolution of stars and their ultimate destinies. Comparing our expectations with real supernova events like SN 1987A and later occurrences such as SN 2011 Fe or SN 2014 J provides critical data for understanding the potential outcomes of Polaris explosion. For example, SN 1054 led to the creation of the Crab Nebula, a cloud that continues to expand and emit radiation across various wavelengths, offering astronomers a rich field for study. Similarly, SN 1987A, observed in the Large Magellanic Cloud, provided insights into the patterns of nucleosynthesis and the dynamics of supernova remnants, including phenomena such as the formation of nebulae and the release of massive jets and changes in luminosity, which can shed light on Polaris' unique characteristics. The formation of nebulae like the Crab Nebula results from the release of material during the supernova explosion, which then interacts with surrounding interstellar gas and dust, enriching it with heavy elements and contributing to the cycle of stellar birth and death. Furthermore, the release of massive jets and high-energy particles rapidly propelled by supernova shock waves has implications for astrophysical processes and cosmic radiation environments. To make a definitive comparison, scientists are evaluating differences in the large-scale composition and velocity of ejected materials between Polaris' anticipated explosion and other observed events. This includes studying the light curves, spectra, and remnants of these events and extrapolating similar characteristics for Polaris' predicted explosion. Assessing whether it might lead to the formation of nebulae or significant stellar dispersions improves our understanding of its potential consequences. Another critical area of study involves examining the pulsational variability of stars nearing their end stages, comparing Polaris against other supernova progenitors. This broader analysis can help estimate similarities or deviations and provide insights into the explosive mechanism. Pulsational variability in stars nearing the end of their lives may be indicative of internal instabilities or imminent catastrophic events, offering clues to the developmental processes leading to supernova explosions. Despite careful observations and extensive research, space experts remain perplexed by the anomalies found in Polaris behavior. Unraveling the unique conditions driving these irregularities holds the key to advancing our understanding of stellar evolution. Understanding the dynamics responsible for Polaris erratic pulsations requires interdisciplinary collaboration, as well as the development of advanced theoretical models and observational techniques. The potential loss of Polaris as a key reference point in the night sky raises fundamental questions for astronomical endeavors. Ground-based telescopes and celestial measurements would require recalibration, affecting the accuracy of cosmic assessments. The absence of Polaris could also impact navigation systems and cultural practices based on celestial landmarks, highlighting the significance of this stellar event. The enigmatic behavior exhibited by Polaris underscores the need for deeper investigations and dedicated research efforts. Astronomers must grapple with the complexities surrounding its erratic pulsations and provide meaningful responses. Recognizing the importance of advancing our understanding of stellar intricacies, the answer to Polaris' fate remains uncertain, and only time will reveal its true nature. Still, the quest for knowledge and understanding in the face of immense uncertainty is a testament to humanity's enduring curiosity in unraveling the mysteries of the universe. The implications of Polaris' potential demise stretch beyond simple astronomical interest. They touch upon the very fabric of how humanity perceives its place in the cosmos. Since the dawn of time, constellations have served as markers of time and navigation, guiding explorers across uncharted waters and lands. The loss of Polaris wouldn't just disrupt traditional navigation methods, but could also have sweeping implications for cultural myths and symbolism tied to the North Star. In various cultures, Polaris has been integral to legends and spirituality. For example, Native American tribes often regarded Polaris as a guiding light in their stories, symbolizing hope and perseverance. Similarly, the ancient Egyptians used the North Star in their architectural designs, aligning pyramids with its position. The disappearance of such a prominent star could alter cultural narratives and the framework of human experience related to navigation and direction. Moreover, the academic community stands to face significant challenges if Polaris were to vanish. Astronomical measurements and observations heavily rely on established reference points. Polaris' role as a constant guide has facilitated the calibration of instruments and models used to study distant worlds, star movements, and even the expansion of the universe. The sudden absence of Polaris would necessitate recalibrating many of these systems, potentially leading to discrepancies in measurements and interpretations of celestial phenomena. As astronomers shift their focus to observing Polaris more closely, new observational advancements are being developed. Progress in spectroscopy and photometry enables scientists to analyze light emitted by stars in extraordinary detail. These tools help identify minute changes in brightness, which are crucial for understanding the mechanisms driving celestial behavior. As researchers gather more data, they aim to refine their models of stellar evolution, particularly concerning stars in the later stages of their life cycles. The study of other similar stars, such as Cepheids and red giants, offers insights that could prove invaluable. For instance, astronomers are observing factors like the period-luminosity relationship, which helps measure distances across the universe. By comparing these stars' behaviors to those of Polaris, experts hope to gain a clearer understanding of stellar dynamics and evolution, further enhancing their grasp of the structure of our universe.